All right, let's dive into a really fascinating technology, one that literally turns wasted heat directly into electricity. I mean, think about all the energy we just lose from our cars, from factories, even from our own bodies. What if we could actually capture all that? Let's find out how.
So let's just start with this. What if you never had to charge your smartwatch again? I mean, ever. No more cables, no more charging pads. And look, this isn't some far-off sci-fi dream. It's a very real possibility, all thanks to the technology we're talking about today.
But, your body heat, that's just a tiny drop in the bucket. We are surrounded by a literal ocean of wasted energy. Just think about the heat pouring out of your car's exhaust pipe, or billowing from those huge factory smokestacks. That's all valuable energy that we're basically just letting disappear into thin air. So here's how we're going to break it all down. First, we'll look at this huge unseen energy source. Then, we'll get into how you actually turn heat into electricity. We'll cover the science behind it, check out some mind-blowing real-world uses, and finally, talk about what's next. Let's do it. Okay, first up, the unseen energy source. Let's really wrap our heads around the sheer scale of this. Pretty much everything we do that uses power, driving a car, running a data center, manufacturing goods, it all kicks out heat that we don't use. It's honestly one of the biggest untapped energy resources on the planet, and it's hiding in plain sight. All right, so how do we grab that energy? Well, that's where things get really cool. We can turn that heat directly into electricity. Meet the hero of our story, the Thermoelectric Generator, or TEG for short. Now, this thing is incredible. It's a solid-state device. All it needs is a temperature difference, a hot side and a cold side, and it just makes electricity directly. There are no turbines, no steam, nothing like that. It's a pure, straightforward conversion. The best way to think about it is like a heat engine, but with a superpower. It has zero moving parts. None. That means it's silent, it's super durable, and there's nothing to break or wear out. And that right there, that's its biggest advantage. It makes it unbelievably reliable, especially when you can't afford for things to go wrong.
So you're probably wondering, how does that even work? Is it magic? Well, not quite, but it's pretty close. Let's dig into the science. It's all built on a phenomenon called the Seebeck effect.
This goes all the way back to 1821. A guy named Thomas Seebeck figured out that if you take a conductive material and heat one end, while keeping the other end cool, something amazing happens. The charge carriers, basically the electrons, start to scurry away from the heat towards the cold. And that movement, that flow of electrons, that is an electric voltage. And what's wild is how simple his original discovery was. He just took two different kinds of metal wire, like iron and copper, joined them up, and heated one of the junctions. And bam, a current started to flow. It's such a beautifully simple principle at its core. Of course, today's tech takes that basic idea and puts it on steroids. Instead of just plain old metal, modern TEGs use these specially engineered semiconductors called P-type and N-type. You can kind of think of them as a team. When you apply heat, one type is really good at pushing electrons away, and the other is great at pulling them in. By setting them up together, you create this super efficient electron highway that massively boosts the effect. You get way more power for the same amount of heat.
All right, enough with the theory. The science is cool, but the real fun begins when we see what this stuff can actually do. And the applications are incredible, from the farthest reaches of space right down to the skin on your arm.
So let's start with about the harshest environment you can possibly imagine. Remember that superpower we talked about, having no moving parts? Well, in deep space, that's not just a nice to have, it's absolutely critical. Think about the Mars Curiosity rover. You can't just send a mechanic millions of miles to fix it. You need something that just works for decades. That's why NASA loves these things. They use radioisotope thermoelectric generators. Basically, a little bit of decaying radioactive material gets really hot, deep space is really cold, and the TEG in the middle turns that temperature difference into reliable power, year after year.
Okay, let's bring it back home, from Mars rovers to something a bit more familiar.
Your car engine is shockingly inefficient. A huge chunk of the energy from the gas you buy is just lost as heat, mostly right out the exhaust pipe. But what if we could reclaim some of that? Imagine slapping some thermoelectric generators right onto the exhaust system. They could grab that waste heat and convert it back into electricity to help power the car. We're talking about a potential mileage boost of up to 10% in hybrids. That's a huge deal.
And that brings us full circle, right back to where we started, your wrist.
Scientists are now making these amazing, flexible thermoelectro materials that you could literally wear.
You can see here how one of these patches generates a real voltage just from the heat of someone's hand. Then you see how that tech gets built right into a glove. Just the simple temperature difference between your warm skin and the cooler air around you is enough juice to power small wearable devices. Pretty amazing, right?
Now, this all sounds incredible, and it is, but it's not perfect. Not yet. So what are the hurdles? Let's talk about the big one, efficiency, and what the future looks like for this technology.
So let's get real for a second. The pros are fantastic, right? No moving parts means they're super reliable, last forever, and make zero noise. But the cons are significant. The biggest one is efficiency. Right now, most TEGs only convert about 5 to 8% of the heat into electricity. On top of that, the best materials can be expensive, and weirdly enough, it's actually really hard to keep the cold side cool enough to maintain that all-important temperature difference.
In the world of thermal electrics, scientists have a report card for their materials. It's called the figure of merit, or just ZT. It basically rolls all the important factors into a single number to tell you how good a material is at this heat-to-electricity conversion. The higher the ZT, the better. Right now, most stuff you can buy has a ZT around 1. The holy grail is to discover new materials that can hit a ZT of 2 or even 3. That would be a total game changer.
But even with those challenges, people are betting big on this tech. Just look at the money flowing in. The global market was just over $300 million back in 2015. By 2030, it's projected to hit almost $1.5 billion. You don't see that kind of growth unless a lot of very smart people think there's a huge future on the horizon. So where does that leave us? Well, whether it's powering rovers on other planets, squeezing more miles out of our cars, or creating gadgets that never need a charger, it's clear we're just scratching the surface of what's possible with this invisible energy source. It really makes you wonder, doesn't it? What else will we power with all the heat we used to just throw away?